Hello and welcome. Today we're going to unpack one of the most powerful and honestly surprisingly common patterns in the entire universe, the normal distribution. You probably know it by its more famous nickname, the bell curve, and trust me, it secretly shapes a huge part of the world around us.
Okay, so let's just jump right in with a question. What on earth could possibly connect something like IQ scores with, say, how long a light bulb is going to last? I mean, they seem completely unrelated, right? But they share this fascinating secret connection.
And the answer is this shape right here, the bell curve. It's this elegant, symmetrical curve that just pops up over and over again. You can almost think of it as a fundamental blueprint for how random things tend to look when you gather enough of them together. So for this first section, let's pull back the curtain. We're going to dig into what this shape actually is and why it's so unbelievably important. All right, so its formal name is the normal distribution, sometimes called the Gaussian distribution. But what this definition really means is pretty simple. For any group of data that follows this pattern, most of the values are going to be clumped right around the average. And the further you move away from that average, the less likely you are to see those values. That's what creates those classic tapering tails on each side.
And believe me when I say it's everywhere. Think about it. Standardized test scores like the SAT, most students land somewhere in the middle. Very few get perfect scores, and very few get super low scores. The exact same pattern shows up for people's heights, for salaries, and yep, even for something as random as the number of light bulbs that need replacing each day in a big building. It's like a natural organizing principle for data.
Okay, so we know what the shape looks like, but how do we actually use it? Well, in this next part, we're going to look at a really simple rule that makes this whole curve incredibly predictable and useful.
This is called the empirical rule. But honestly, you can just call it the 68-95-99.7 rule. It's this awesome mental shortcut that tells you exactly how your data is spread out, all without doing any complicated math.
Now, the key to this whole thing is a concept called standard deviation. Don't let the name scare you. Just think of it as a standard step, or a fixed amount of distance away from the average, which is right in the center of the curve. The empirical rule uses these steps to predict exactly where most of the data is going to be.
And here's the rule itself. It's so neat. About 68% of all your data, that's the huge majority, will fall within just one of those steps from the average. Go out 2 steps from the middle, and boom, you've captured 95% of everything. And if you go out 3 steps, you've got 99.7% of the data. That is practically everything. It's just so consistent.
Okay, knowing how data is spread out is one thing, but what if you want to compare two completely different sets of data? For that, we need a special tool that statisticians call the z-score. Honestly, the best way to think about it is as a universal translator.
So here's a classic problem that shows why this is so helpful. Let's say you get a 90 on a math test and a 95 on an English test. At first glance, you'd think the English score is better, right? I mean, 95 is higher than 90. But wait a minute. The raw score doesn't actually tell you the whole story. The really important question is, which grade was better compared to everyone else in the class? To know that, you need more context. You need to know what the class average was, and you need to know how spread out the scores were for each of those tests.
And this is exactly what the z-score does for us. It takes any score from any bell curve and translates it into this one universal language so you can make a fair comparison. It tells you precisely how many of those standard steps your score was away from the class average. So let's say it turns out your 90 in math was 2 whole standard deviations above the class average. That's a z-score of 2. But your 95 in English was only 1 standard deviation above its average. Suddenly, that z-score tells you your math performance was way more outstanding compared to your classmates. And that right there shows you the power of the z-score.
So whenever you're faced with one of these problems, the process is pretty straightforward. First, and I can't stress this enough because it's where people make mistakes, always sketch the curve. See the problem. Then you calculate the z-score to standardize everything. And from there, you can easily look up the exact probability. That first little sketch just makes everything else click into place.
All right, to wrap things up, let's zoom back out and talk about why this whole concept is so much more than just a neat little trick for statisticians. The bell curve gives us a real framework for understanding the world. It lets us look at a bunch of data and figure out what's normal and what's an outlier. It lets us calculate the odds of something happening and make much smarter decisions in really important fields like finance, medicine, and research. It's a tool for finding the signal in the noise. And if you want one last mind-bending idea about how fundamental this is, check this out. The Levy-Cramer theorem basically says that if you add two random independent things together and the result is a perfect bell curve, then both of those original things you started with had to have been bell curves themselves. It's not just a result, it's its own building block.
So you see, the bell curve isn't just some convenient pattern we happen to see sometimes. It's a deep mathematical truth about the way randomness itself is structured. It's a fundamental property of the statistical universe.